So we already had the polygon unit, right? We did decagons and octagons and septagons and heptagons. Those are the same thing. Nonagons. So we've studied polygons, but we haven't found the area of a polygon. Today, we're going to find a formula. We're going to be given a formula. And just be careful because it does only work on regular polygons. So if you were, just playing devil's advocate, if you were given like an irregular polygon, I don't know, that was weird, then you would have to divide it up into different shapes that you know how to find, pretend, you know what I mean? So what the formula we're going to develop today only works if the polygon is regular. Okay, so let's talk about 3 words that are really integral to this lesson. Word number 1, regular polygon. Don't write the definition down because you already know this. A regular polygon is a polygon in which all sides and all angles are congruent. So tick mark on every side, arc on every angle. Okay, new word. So you can write this one down. Apothem. That's how you pronounce it. Apothem, like apple. So not apothem, but apothem is technically the correct way to pronounce it. I'm not going to lie, the first like 5 years of teaching I called it an apothem. So I won't get mad at you if you call it that. So, what in the world is an apothem? An apothem is the perpendicular distance from the center of the polygon to a side. From the center to a side, and it hits the side at a 90-degree angle. Kind of like an altitude, but it's not an altitude. But they both start with an A. So an apothem, center to side, and it has to be perpendicular to the side. I'll give you a minute to write that down and draw that picture. Okay, we have another word to go over. I know that we have talked about a radius before in the context of a circle, but I bet you didn't know that polygons had radii. So a radius in the context of a regular polygon is the distance from the center of the polygon. Well, that's the same as up here. From the center of the polygon to a vertex. So from the center to a vertex. And since these are regular polygons, it is always going to bisect that vertex, if you're wondering. The radius will bisect the vertex because these are regular. Okay. Okay. I know we threw around the words inscribed and circumscribed last unit, but we didn't really test you over it. We didn't really hold you accountable for it. So this unit, and today, starting right this moment, we're going to need to make peace with those words, inscribed and circumscribed. So when you hear inscribed, I want you to think inside. Inscribed, inside. And when you hear circumscribed, I want you to think outside, just because it's the opposite of inside. So inscribed, inside. Okay. There are 2 different ways to say this. The pentagon is inscribed in the circle. The circle is circumscribed about the pentagon. So it depends on which shape we're talking about. But if I'm talking about the circle's on the outside, so it's circumscribed. When I draw the radius of my circle, not all of the radii, but when I draw a particular radius of my circle, it's also the radius of the pentagon. So the radius of the circle is the radius of the pentagon. You're like, where are you going with this, Miss Stanton? Conversely, if I draw the inscribed circle, so we've got a circumscribed one, and we've got an inscribed one, the radius of the circle is the apothem of the pentagon. The radius of the circle is the apothem of the pentagon. And someone said they played I Spy, and they found our favorite shape in the whole world. They found a right triangle. I want you to draw that right triangle in your notes. You don't have to draw my whole picture. Just draw the right triangle because this triangle is the most important part of the lesson. You really do love them. That's sweet. So, in my right triangle, this leg is my apothem. The radius is my hypotenuse. And what's that third side? What's that other leg? What variable would I give it? Not really going with the trig theme yet. We're doing, so we've got an apothem, we've got a radius. Ooh, good. This is a side of my pentagon. But that leg is not a side of my pentagon. It's half of a side. So put the picture of that triangle in your notes. Very important. All right, let's look at a few things that could happen. So I want you to compare and contrast these pictures. We really care about one being a triangle and one being a square. I don't care about that. But take a look at when the circle is outside versus when the circle is inside. Circle is outside versus when a circle is inside. Notice when the circle is outside the regular polygon, the radius equals the radius. I'm not going to underline it. I'll just read it. When the circle is inside the figure, the radius doesn't equal the radius. The radius of the circle is the apothem of the polygon. Whether it's a square or a nonagon, it doesn't matter which one. So this works for any regular polygons. I just chose square and triangle to keep it simple. Okay? So notice, when they meet at the vertices, they're meeting. That's where the circle is meeting the triangle. When they meet at the vertices, that's when the radii match. When they meet at the sides, that's when the radius becomes the apothem. You don't need to memorize what's on this slide, but you need to be able to draw a picture. Once you have the picture, you'll know if the radius is the radius or the radius is the apothem. So once you have a picture, you'll know. Okay. There are three special cases. When I say special cases, what I mean is, when you have a right triangle and you're missing, let's say this is 9 and this is x. When you're missing two of the sides, can't use Pythagorean theorem, you could either use 30, 60, 90 if it's special, or you have to use trig if it's not special. So what we're going to look at, I'm just going to go ahead to the summary slide. We're going to look at the three cases that are special. 30, 60, 90, 45, 45, 90. Anything else, nonagon, heptagon, decagon, pentagon, anything else is not special, and you have to use trig. So I'm giving you time to write the special cases down in your notes. Put the special cases there with the angles as well. The not special cases, you have to use trig. So I'm giving you time to write these down. These are the special cases where your answer can still be exact. In all the other cases, your answer is not going to be exact because you're going to have to use trig, and when we use trig, we round. Notice where the 30 and the 60 are in the equilateral triangle and the hexagon, because students get mixed up where to put those angle measures. To me, it's like common sense, right? Because in this hexagon, that's an obtuse angle. You divide an obtuse angle in half, you don't get 30, you get 60. So anyways, you're writing these down, drawing them. We'll finally get to the formula on the next page, I promise. I mean, it's on your formula chart, but anyway. It's time to reveal the formula. I would only write down the area one. The perimeter is kind of common sense, right? You take how long a side is and you multiply it by the number of sides. So don't spend time writing down the formula for perimeter. The formula for area is, now you're going to have to pay attention to capital and lowercase here. Capital A stands for area, equals lowercase a, apothem, uppercase P, perimeter, divided by 2. Apothem times perimeter divided by 2. We are armed with a formula. We are armed with all of our background knowledge. Now we can try a problem. Find the area of a regular hexagon inscribed in a circle with a radius of 4. So when you see a problem like this, I want you to think, you don't have to cross it out like I am, but I want you to think inscribed means inside. So we've got a hexagon inside a circle. So you can draw the circle first or draw the hexagon first. It doesn't matter. Don't judge. This isn't going to be equilateral. It's not going to be regular. Best I can do. All right. So, oops, we've got a hexagon, and it needs to be inside a circle. So the circle needs to hit every vertex. Cool. Hexagon, inside circle. Inside a circle with a radius of 4. Who does the radius belong to? It belongs to the circle. So the circle has a radius of 4. Would I draw that radius? Just want to play devil's advocate, just want to make sure you know. No, that radius would not help me solve this problem. Instead, I need to draw the radius of the circle that matches the radius of the hexagon, and then I'll have enough information to solve. Okay, the radius is 4. Find the area. Let's dive right in, guys. Every time you are going to draw that cute little triangle that's made up of the apothem and of half the side and the radius. So every time you're going to draw that cute little triangle. The first few examples are going to be special cases. So this is a special case, meaning we don't need to use trig. We need to use 30, 60, 90. Make sure that you put the angles in the correct spot. The 60 goes here, even though that's hard to see, and the 30 goes here. If you need to go off to the side and do this, you do it. But if you can just put it on your picture directly, you don't have to draw out the table every time. 4 is across from 90, so 4 is our 2x. Our x is 2, and 2 root 3 goes across from 60. So this is our apothem. This is half of our side. Perimeter. Type the perimeter in the chat. What's the perimeter? 24. Very good. So one of our sides, each of our sides is 4. There's 6 sides, so 4 times 6. So the perimeter is 24. The apothem is 2 root 3. Apothem times perimeter divided by 2. The 2's cancel, and our area is 24 root 3 centimeters squared. Find the area of an equilateral triangle with radius 6 root 3. All right, so let's draw it. An equilateral triangle, that's a regular polygon, with radius 6 root 3. So now we have the option, when we are given a triangle, if it's equilateral, to do, well, we could do base times height divided by 2. We could do side squared root 3 over 4. Or we could do our new formula. So it's going to depend on what information you're given, and you just choose the formula that's most appropriate to the information, okay? We need to label our angles, 30, 60. 6 root 3 is across from 90. I'm going to cut it in half. 6 root 3 was our 2x, so our x is half of it, 3 root 3. And across from 60, let me go to the side, is x, that's my x, root 3. X root 3 is this. I need to simplify that. That's 3 times 3, which is 9. Can you put this in your calculator? Absolutely, you can put it in your calculator, okay? You have permission. Now be careful. This is what students do. They go and they think that the side is 9. So be careful. We didn't find the side. We only found half of the side. Okay, I think we're ready. What's the perimeter? Who's going to type it first? 54, very good. So we've got apothem times perimeter divided by 2. In your calculator, you do 3 times 54 divided by 2. You ignore the root 3, and then you multiply back through at the end. You ignore the root 3, and you multiply back through at the end. So the answer is 81 root 3 meters squared. All right, we're going to skip to number 5. We've done enough special cases. I know you can work with those special cases. Now I have to teach you how to work with one, for example, a pentagon, and this one is not a special case. What were we given? What does that 6 represent? The apothem. Very good. So we draw our cute little triangle that we always draw every time. We have the apothem. That's nice. Now we need the perimeter. That's the only other thing we need for the formula. So I'm going to put an X there. I can't solve this triangle right now. You can't do trig with one side. Doesn't work. So what we need is an angle. What we need is an angle. Here's what I recommend you do. How many degrees are in a circle? 360. Okay? Now, if I were to take 360 and divide it by the number of sides, if I take 360 and divide it by 5, I'm going to get that angle right there. This angle is 72. But I don't want that big angle. I just want this angle right here. So I'm not going to do 360 divided by 5. I'm going to do every time 360 divided by not the number of sides, but double the number of sides. Because if I were to draw triangles all the way around, there'd be 2 triangles per side. So I would end up drawing 10 triangles if I kept going, but we're not going to mess up our picture. So that's really just 360 divided by 10. So I know that that angle is 36 degrees. So this angle is 36, this is 6, and this is X. I have opposite and adjacent. So tan 36 equals opposite over adjacent. The variable is in the numerator, so we're going to multiply 6 times tan 36. So I'm going to my calculator. 6 times tan 36. And I get 4.359255. I know you can't see that because my screen is backlit. Okay, don't write that number down. Don't do it. I'm going to keep that number in my calculator if you can follow me, okay? That is this. That is half a side. Now I want it to be a whole side. So everyone do times 2. Now it's a whole side. But there's 5 sides. So now do times 5. Okay, what's that? Now I have the perimeter. But I need apothem times perimeter divided by 2. So I'm going to do times 6. There's apothem times perimeter. And now divided by 2. You're not required to write every step down. You can go to your calculator. Grand total of 130.8 because it said nearest 10. Do not, here's what not to do. When we found X was 4.359. I bet if you use that decimal, you would have been okay. But if you write down 4.3 and then you solve, your answer will not be correct. So what I'm saying is that do not round in the middle of the problem. Keep the decimal at least 3 places. Keep the decimal and round at the very end. So just a reminder that these are our special cases. When we use 30, 60, 90, our answer will be exact unless they tell us to round. These are our not special cases where we need to use trig and our answer will be rounded. That symbol means approximate. It'll be approximately the right answer. So when we have our not special cases, you need an angle. You can't do trig without an angle. So since you need an angle, you can pick whichever strategy works best with you. If you remember, to find an angle of a regular polygon, you did n minus 2 times 180, which was the sum of the interior angles. Then you divided it by n, and that got you one angle. But notice, in this triangle, we don't want the whole angle. So that's why you need to cut it in half, divide it by 2n. So that's a strategy. I don't personally ever use that strategy. I think that one's a little bit harder to memorize. But if you remember that formula for previous unit, then go ahead and use that strategy. What I like to use is the idea that if I start here and I rotate around full circle, I've rotated 360 degrees. And I can divide that by the number of sides. If I divide it by the number of sides, I get this angle right here. But I don't want that whole angle. I only want half of it. So you divide it by double the number of sides. So let's play with that. I give you a nonagon. Find the missing angle. Okay, 360 divided by 18. And I would have this angle right here. I give you a decagon. Find the missing angle. 360 not divided by 10, but divided by 20. So hopefully you see how that works, because in order to do trig, you would need that missing angle. All right, find the area of a regular octagon, circumscribed about a circle with a radius of 5. So I'm going to have the picture right here for you. So it's a regular octagon, and when you see the word circumscribed, it means outside. So it's an octagon outside of a circle, and the circle it's always the radius of the circle. The circle has a radius of 5. So here's what I could do just as I'm beginning. I try to draw my normal radius that I usually draw, and oh no, I'm not touching my octagon. So that's a great radius of my circle, but it does not help me with my octagon at all. So I'm like, okay, don't want to draw that one. So then I draw another one. That radius of my circle is really the apothem of my octagon. So now we're done with the circle. We don't need the circle anymore. That was just to figure out where to put that segment. So it says that the segment is 5. Okay. So, like I said, the circle was just being used to figure out where the segment goes. Now that we have our apothem drawn in our 5, then we do not need to look at the circle anymore. We draw our cute little triangle. In the formula for area of a polygon, you don't need the radius. R is not in the formula. So we are not looking for the radius. We are looking for the side, because the side is going to get us to our perimeter. All right. This is a trig problem because it's not special. So we need to find this angle right here. The way that we're going to do that is 360 divided by 16. Because an octagon has 8 sides and there's 2 triangles per side. So 360 divided by 16, and we get 22.5. Don't be alarmed that it's a decimal. It's okay. All right, trig time. Tangent again, because we have opposite our angle and adjacent to our angle. So it's TOA. Tan of 22.5 equals opposite over adjacent. My variable's in the numerator, so I'm going to multiply 5 times tan 22.5. And I get 2.07, on and on and on and on, this long decimal. So I'm not going to write it down. I'm going to keep using the whole decimal. This, in my calculator, is half of a side. Times 2. Now I have a whole side. Times 8. Now I have the perimeter of my octagon. I'll just write it down just to show you, just in case you're getting confused by everything being done in the calculator. Okay. I can still keep using my calculator. In other words, the formula says perimeter times apothem divided by 2. So I've got my perimeter. Now I need to do times 5, because that's my apothem, divided by 2, because that's what the formula says. And the area of my octagon is 82.8. They didn't give us units, so we don't have to give them units back. So just in summary, a few things to remember. Inscribed means inside, circumscribed means outside. If you have a triangle, a square, or a hexagon, those are special cases, 30, 60, 90, 45, 45, 90. If you have anything else, you're using trig, and you're doing 360 divided by double the number of sides. That will find you your angle, and then you go from there. Do not round as you go, round at the very end of those problems.